We were on still in P2P, and P2P uses a technology called distributed hash table. And so I wanted to discuss that briefly. Everybody probably knows the hash table is that if you have a key that you want to look up in a table, you could keep a very big table and every key will have its own place. If the key is 10-bit long, you could keep a table which is 2 raised to 10-bit long. If the key is 32-bit long, you could keep a table which is 2 raised to 32-bit long. If the key is 128-bit long, you could keep a table which is 2 raised to 128-bit long. But that would be a very long table. So if the key is big and the table is small, the way we do that is by using a hash function. What hash does is, hash is a function that maps a big key to a small key, a big number of bits to a small number of bits in a very unique way, so that two big keys will not really clash and hash to the same value. They could, obviously, because if you are going to take 128-bit and hash them to 10 bits, two 128-bit quantities could hash to 10 bits, but the probability is small. We just somehow, a good hash function will reduce that probability. A bad hash function could take all 128-bit quantities and put them into the first cell right there. Just hash everything to 1. Right? That would be a really bad hash function. And a good hash function will try to be such that all these cells, if you have a table which is 10-bit long, all the cells will be used up. And if you have 2 raised to 10 keys, if you have more keys, then obviously none of the hash function will be able to avoid the clash. Right? So your table has to be of the size similar to the number of keys that you are really going to use. And so if you are going to use only 5 keys, the table doesn't have to be 50 of size 50. It could be maybe 8, 16, something like that. And so what do? So we use a hash function to reduce the key size, and we look up that hash in the table. So let's say hash says number 10. So you go to the 10th entry, and then you look up the key there where the exact value is stored, and you match. If it matches, you got the right entry. And for that entry, you might have other things, such as if it was the name of a person, it will have a social security number, their bank account number, and so on and so forth. So that is what you use the keys to look up, right? You are using the whatever you are using, maybe social security number or name. You hash it to a number, and in that entry of the table, you expect to find everything, right? It is quite possible that the key doesn't match, because another key had already occupied that position. So then there are ways of finding the next location where that you should be. Generally, simplest thing is to just look at the next location. If the key matches, it doesn't, then go to the next location until you find a match. Generally, hash is so good, and your key table is sparsely populated, and this table is sparsely populated such that you should be able to find the match on the very first location. So is it clear as to how the hash tables work? Right? You take a big key, hash it to a small number of bits. That gives you the index of the end table entry, and if not that one, maybe the next one, maybe the next one, maybe the next one. Right? So you reduce the searching time. The biggest thing is there is no search, because otherwise you can do a binary search. You could arrange the table in an ordered key manner, because sort it out. Sorting is a long operation for these things, and then you go through binary search, which take log to n, where n is the number of entries. Operation, but hash just gives you right away in one operation. And let's say hashes are used whenever you have large size keys to be looked up into a small size into a table. All right, so let's see, we have covered everything. Hash tables are used to find an entry in the table, distributed hash tables. Now, what if the table is so big, like a DNS, domain name server, which is a big table, and not everybody has a complete table, so the table would be distributed, right? So what you need is a distributed hash table, DHT. Distributed hash table means that you may not, one computer may not have the whole table, and it may have to go to some other table to look, some other place to look it up. So we'll talk about the distributed part in the next slide. But database is partitioned and stored in many peers, many computers, has the key to the peer, to find the peer that has the key, and then the peers are numbered from 0 to 2 and -1, and therefore the keys are numbered similarly. And so basically what you are doing is, if you want to find a file, every file has a key, right? So you want to find out who has all the information about this particular file. So you hash that and you find the peer, right? So one way to organize a distributed hash table, DHT, is a circular way. So this node has all the information about the keys that begin with 0001. Well, let's assume simplicity like that, but it is not always that simple. So let's say this is 001, this is 3, 4, 5, 8, 10, 12, 15, right? Obviously these, this is like this 1, 3, 4, 5, 8, 12, 15. So since number 2 is missing, 2 will be with one of these two with some kind of formula which says that 2 will be either with this or 3, and then 4 and 5 and 6 is not there, so 6 will have to be divided. So somehow the keys have to be divided among the people who are present. Okay, and the people do come and leave. That's another problem, is that 12 is there right now but probably can leave at some point. People are going to shut down their computer when they want. So basically people have to find out who has the key. So first thing we do is we hash it. We hash it and we find out that the number hashes to 12. Well, 12 is there. Let's say number hashes to 11. So it is quite possible it hashes to 12, then we can just go to 12 and say, look, this key, I want to look it up, can you tell me the information? And that's easy because 12 is alive and well and has all the keys beginning with 12. But 11 we are not sure, and so just like the before, we hash it and we go to 10. Suppose it hashes to 11, we go to 10 and say, do you have it? 10 says, no, I don't have it, maybe somebody else has it. And so at that point there will be search, linear search. Just like we did the linear search before here, but the first entry we know where to start. Here we know where to start, and then we do a linear search. And we could keep a complete link to all of these nodes, in which case this will be the number 3 knows about 10, 12, 11, 15, all of these nodes, but it will have lot of things to remember. Or it could just remember 2 numbers, it could remember 1 and 4. And it could ask 4, what do you, can you find out who has the key 11, and then 4 could ask somebody else. So if you didn't keep any other links, you just can go in circle. 3 will ask 4, 4 will ask 5, 5 will ask 6, 6 will ask 7, and so on and so forth, whoever is alive, right? That will be a lot of time taken to resolve the hash. On the other hand, you could keep more than 2 links. 3 could keep the link for 1, 4, and 8 and 12. Alright, in that case it could go straight to 8 and say, do you know where is 11 key stored? So there is a trade-off of memory versus time. More storage you keep, more links you keep, the less time it takes. But in the simplest case, you just keep, minimum you need to keep 2 links, your predecessor and your next one. And everybody is organized in a circle. And there are many other methods of distributed hash table. This is a topic of research, People have come up with many other methods and optimizations of how to minimize the time and the number of messages and so on and so forth. Yeah, your question?
Yeah, so is this basically sort of like a nested hash table in the sense that first you're searching for a node and then you're searching for a key?
Yeah, inside the node, they probably have another hash, and that's the simpler part. That is more like this. This slide is about distributed hash table. So you are looking for a node.
It's not like one big table that's split into parts. It's more like you're doing two separate operations. First find that node and then find the key within.
Well, it is used for both. Actually, I think it is a big table, because when you want to store the key, you do the same thing. You want to find out where should it be stored. You don't want to store the key. You find out where it should be stored and tell that node, now store the key. When you want to look up, you look up the key from that node. So it is one big table. Is it clear to everybody? Right? That this is one big table which is divided by some formula as to where it should be, and the main problem is that even though we say 11 should have it, but 11 is not there, so somebody else has to keep track of it. So that is the next thing, is that peer churn, is that as the peers leave, we have to keep track of who is alive, who is taking responsibility for what. So when a peer leaves, each peer keeps track of their first and second successors. So for 3, the first successor is 4 and the second successor is 5. And they poll each other, basically. So 3 knows when 4 leaves, the answer doesn't come back, and then it knows that, okay, 4 is gone, so then it says 5. Look, 4 is gone, I am now your successor, and then who is the next successor, then you will know that 3, 5, and 8 are now there. Right? So they keep track of who is there. So you keep track of your first and second successor. You do periodic handshake to verify connectivity. So you say hello, and then the hello comes back, so you know that it's still there. When the first successor leaves, you connect to the second and you find a new second, right? And when a new peer joins, it sends a message to peer 1, which gets forwarded until the right predecessor responds. So when somebody comes back, suppose somebody comes back here, then it will send the message to number 1, and it will go to 1, 2, 3, 4, 5, and they say, oh, you are position 14, so you just join here, your next successor is 15, and next to next is 1. So you are placed in the right place in the table by some algorithm. Okay? So when a new one comes in, they find their place. When somebody leaves, the other people who are left, they really join together so that the whole thing remains connected. All right. Yeah, go ahead.
So first and second successor leave simultaneously. Is there another?
Yeah. So there is a problem. I mean, it's quite possible that 2 successors can leave. Then they will basically start, initialization problem where now, I don't know who to talk to. Then when 1 says to 3, when, hello, then it says, well, I don't have any successors anymore. Then it might go backwards, or they will restart the whole organization to figure out who is left. And so the whole circle will be rebuilt from the scratch. Right? If 1 leaves, that becomes a problem too, because everybody is going to go to 1 when they want to join if 1 is not there. So hopefully 1 is something which is more stable and not like everybody else who is leaving. So yeah, so there are technologies or there are algorithms for rebuilding and algorithms for starting initialization. Yeah.
Don't you also lose data when people leave because they had like the data that they saved that you were looking for?
Right. Now, so people when they leave, the question was, what happens? Do they give the data to you and then they leave? Yes, that would be nice if they did that. So for example, if 4 could tell 3 and 5 that, okay, I have the data, I'm going to leave, but most people don't tell.
You replicate it to the next one, so you both have it.
Yeah, right. So there's no, see, all those things could be built, but generally when people leave, they leave.
So you lose the data.
So you have to be ready for a crash, right? So the system has to be designed so that the data has to be reconstructed, somehow the keys will have to be rebuilt. And so when somebody says, well, where is the file number 5? It is 4 is responsible, but 4 just came up. You say, sorry, I don't know yet. Right? And then somebody finds 5, and then they say where to store 5, they find 4. And so this is a continuous process where the answers are not perfect. And remember, this is done only for very large databases. These are very, very large databases. And there is a large dynamics, there is a large changes going on, people coming in and out. All right, so that is about P2P. Let me see, I think we already talked about BitTorrent in a detail, and we said that P2P is better because it reduces the delay and it distributes the traffic better than client server. And then we talked about you need hash tables to maintain this P2P stuff. Any question about P2P before we change the topic? If none, then we talk about one more interesting part of networking that is called NAT. And NAT actually came about around 95 or 91 time frame when internet suddenly started expanding and we ran out of addresses. And so somebody said that why don't we have some addresses which are recyclable, which can be used by everybody. So those are called private addresses. Private addresses are like 192, anything that begins with 192.168, not 192. 192.168 is private. 192.169 is not private. 192.167 is not private. 192.168 is private. Remember that, okay? That would be an exam question. So, any organization can use the number without asking anybody. You don't have to go to IANA and say, can I get an address? You can use in your home 192.168, and all of you are using 192.168 in your home, right? And so that is a private address. The only restriction on the private address is that you cannot use it on the internet. If you send a packet on the internet with address starting from 192.168 or address going to 192.168, it will be just thrown away. It's a private address. It can be used only in the private network in your own home. Inside the home, you can have lots of computers with that, starting with that address. They can talk to each other. But when you want to go out, you have to use a public address. Yeah.
So is there a particular reason 192.168 from the network?
Why it picked up that number?
Yeah, why can't they choose other numbers?
Oh yeah, they could choose any number, but those numbers were available at that time that were not assigned to anybody. So they could not choose, for example, 128.252 because that was assigned to Wushtel. And if we made it private, Wushtel has to get rid of all its addresses. So actually, this is not the only private address. There are 3 private addresses, 192.168, and I forget, I think 172, and there is one more. So, but 192.168 is most common, so we all remember. So there are 3 sequences which are defined for private use. There is one, I think 10 dot something also is private. But those happen to be the addresses which were available at that time when they made this decision. There is no other significance to this. Yeah.
So, but we should just memorize the 192.168. We don't have to memorize all the different blocks.
Well, when it comes to it, actually this NAT thing has come up totally out of sequence because the way this book is top down. Generally, we teach bottom up. So we talk about the whole addressing thing, and there we can go through the whole thing. So when we go to IP, layer 3, there we will have all 3 numbers, and that time you should probably remember. But right now you just need to know the function and know 192.168, because the function is that this is a private address and you can put 0, 1, 2, 3 after that, or you can put 1, 2, 3 to 255. So you have 255 times 255, 2 raised to 16 addresses available to you, right? Because you can put anything in the last 2 digits. But when you go in the public domain, you have to use public address. And that means you should have at least one public address. So everybody needs one public address. So in your home, you have one public address. right? WashU has 2,000 public addresses. Actually, WashU and all the US universities are lucky ones, because when the addresses were being given out, there was nobody else, so they all got 2 raised to 16 addresses. Some universities got 2 raised to 24 addresses. Now you cannot even think about 2 raised to 24 addresses. Harvard probably has 2 raised to 24 addresses. But so as the universities came later and later in the game, they started giving 2 raised to 8 addresses, and then they started giving 1 address. Now 1 address is difficult to find in some countries, because those came much later in the game. So US is in some sense, that's why it has unfair advantage of being the leader, because we invented the technology, and so we got all these addresses and names which were for free. And other countries are complaining, obviously. So, but the idea is that you need at least 1 public address. Every organization needs 1 public address. And every home in USA needs a public address. Every home in China needs a public address, right? So you can imagine the problem in China, right? And problem in any other country. Name your country. But in USA, we luckily have public addresses. However, there are not that many public addresses, so we get dynamic addresses, in the sense that your carrier, AT&T or Verizon, gives you the address when your computer is up. When it goes down, it gives it to somebody else. So they are also recycling the same addresses. Yeah.
Didn't like IPv6 solve this problem though? So
yeah, but IPv6 is not here. Do you have IPv6?
I mean, most computers have it built in now.
Yeah, most computers have, but no routers have. And so the problem is you can't use it. Have you used IPv6? No, nobody has used it. So that's the problem. See, the thing is, IPv6 is here but not here. And so this is actually solve the problem. The real solution to the address shortage is NAT. Is this network address translator takes your inside address and translates it to the outside address. And anything coming from the outside is translated back. Yeah.
How do you know which computer?
Yeah, right. So I'm coming to that. I haven't described as to how it works. I have just described that there are 2 kinds of addresses, private and public, and the NAT is the one which does the translation. How does it do it? So basically, let me first go line by line here and make sure that I have done everything before I come to how does it do it. So it can be used by anyone and cannot be used on the public internet, that we said that. NAT overwrites the source addresses on all outgoing packets and overwrites the destination addresses on all incoming packets. So anything that comes, now the question still remains, how does it know which computer it is going to? There are 15 computers inside. But if suppose it find out that, yeah, this packet is coming in, so which address it should go to, if it knows that, it just writes that address, and once the packet comes here, it goes to the right place. All right? And the way it does it, and this is where it is little bit out of order, in the sense that when we go to IP addresses, then we can exactly tell you what it is. But right now, I'm going to try my best. Is that whenever some packet goes out, NAT remembers what was the source port number and what was the source IP address. It changes the source IP address to this number, and it changes the source port number to some other number, and it makes a table. It says, okay, I put this port number for this address and this port number. See what I mean? It remembers that for all outgoing packets. When the response comes back, the response says to this address, and to that source port number now becomes the destination port number. Right? When the response comes back, it looks at the destination address and the destination port number, looks up in that table, and finds the right address and the port number. So it actually overwrites both the address and the port number, and then the packet is good to go.
So
yeah.
they all have different source port numbers, right?
Okay, so it doesn't matter. The question was, can they all have the source port number 80? The answer is yes. So this one sends out a packet that says my source address is 02 and my source port is 80. And this one sends out that my address is 04 and my source is 80. This will give two different source port numbers. The NAT will give two different numbers and put it into table. It will say, oh, I gave him 3081 and I gave him 3082. Right? When the response comes back to 3081, it knows who it is for, right? Does that answer your question? Yeah.
So that means like if all of them, the NAT would have to make, when it sends one out, it has to
Make up a unique number.
Yeah, so everyone's communicating all at the same time.
Yes, all of them are communicating on all the ports at the same time. Hopefully not all the 2⁻16 ports are used up, otherwise that would be a real tough one. In that case, you will really need, that's not a big problem, but if you have so many computers, you probably need more than one address. Then you have, for each address you can have a table. Right? So suppose you have two addresses, you can have two tables. If it's coming to this address and this port, here's the table. If it's coming to that other address, there's the other table. Right? So for large networks, you really need more than one public address. This is good for small networks. One address is good for small networks. All right, so now you are using, all of you are using NAT. Actually, when in your home, nobody has public address, and in the university, we all have public addresses. Believe it or not, this is a luxury. When you log in into wireless today, you get 128.252. That's a public address. That's a luxury that is not available in many countries. And it is going away in the sense that more and more, even WashU and other universities are using private addresses. Simply because the addresses are not there. That many addresses are not there. So sometimes when you log in as a guest, you get 172 point something. That is a private address. Sometimes you get 10 point something. That is a private address. So anyway, so this is NAT. Everybody understand NAT? And that it works okay, right? All right. Final thing is Skype. So Skype is actually stands for Sky peer-to-peer. Sorry, go ahead. Yeah, question.
Explain again about the inside, like WashU, you have a public address.
Yeah, well, inside WashU we use both public and private addresses. Most of us get public address when we log into Boofy or something like that, Boofy S. But if you go into Boofy Guest or something, they give you private address, 172 point something private address.
So this is like a network which gives you a public address?
No. See, what they do is they keep everybody who is a guest into a private network. So their packet will go through a firewall and through a NAT box. All right, this is private. And otherwise, we have public addresses. I can talk directly to anybody. Anybody can talk directly to me.
Which network gives you the public address?
Boofy S.
Which is affiliated with my username?
WUFI-S. Secured Washington University Wi-Fi. I'm sorry, what did you say? Was the comment there?
I just tried it, like connected to get a private address. It's the 170.
Yeah. Because they want to keep. So basically, here's the thing. They are now putting in more and more firewalls. Up until last year, every computer in my office had a public address, and I could log in from outside. But now what they have done is, even though I have public addresses, some of them, so the thing is, public addresses, I have to make a special request. So they gave some public addresses for my things that I need to access from outside, such as my cameras, such as my printer, such as my whatever servers. And those are even inside the firewall. So the firewall doesn't mean that you cannot put a public address and a firewall. So public address and a firewall. So now first I have to do VPN, and then do it. Yeah.
I think the rule is if you log on with a CEC account, you get a public IP address. If you have just CEC, you get a private one.
Okay. All right. So what he's saying is that the CEC people are less trusted. CEC is student network, and therefore you get the private address. And if you have a research account which is CES, then you get a public address. So as I said before, whether it is Boofy S or this thing like that, the addresses, private addresses have restrictions by design. They can't go without NAT. Public addresses have less restrictions, although you can still put a Wi-Fi. All right, so is that clear now? Private, public, NAT. All right, Skype. So Skype, actually, you didn't know what it stands for, but Skype stands for Sky Peer-to-Peer. Okay, it's a P2P technology, and the way they started is that your computer connects to somebody else's computer who has agreed to be a super peer, and then they forward your calls to somebody else that you need to go to. So there are similar other networks for faxes and other things, and obviously many of these super peers might as well belong to Skype company as well. I mean, they don't have to really, if they can't find a volunteer in some places, they can just put their computer and be done with it. But so when somebody joins, they find the nearest super peer, they join with them, and they tell them that, look, I am up, and then there's a distributed hash table and everything else to figure out who is where and how to find them. Okay, if you are inside a NAT box, if you are inside a private network, then obviously here's the problem with the NAT. I should probably go back to this one, last line. NAT doesn't allow you incoming connection. It only allows you outgoing connection. What it means is if you don't go out, nobody can come into you. So when you send a request, the response comes back, but request cannot come back. So suppose you put a web server here, somebody sends a request to this address, port 80, and this port 80 is not in the table, it will not go. But obviously we can make an exception and register all port 80 requests will go to 02. You can make that, and your router can remember that. So you can do port forwarding, right? That is called port forwarding. Then nobody else can use port 80, by the way. Nobody in your network can use port 80 because all port 80 requests will be forwarded to that node. Then the outside request can come in. Otherwise, we have to have the port number, outgoing port number, before we can have incoming port number. All right. So NAT means only incoming requests, outgoing requests are possible. You cannot have a server without having port forwarding, which means nobody else can have that port. So port forwarding is clear, right? That you have to get somehow on the NAT table, and one way to get the NAT table is that you send a request and you automatically get on the table. Another way is that you register permanently. All right. So how does Skype get into you? Well, basically, the way Skype gets is that you open the port 80 or whatever, and you make a request. So now you have a connection set up. Once you have the TCP connection set up, then you have request response going. So when a call comes to you, it is not a new request. It is basically in response to your initial registration thing that you had sent a message out. The NAT remembered that you have sent a message out. Everything comes back on that port. So the incoming is possible only when you start the outgoing first. Yeah.
So when you send the outgoing, is that basically going to Skype Skype server somewhere.
Yeah.
And then after the connection's made, do things still go through Skype, or is it able to just back and forth?
Right. Now, so the question is, if this wants to find out where I am, it has to go to server to find out, and then it finds out that I'm connected to that server, so that server sends me a request. So the request goes to me through that, from that server, right? At this point, I can send a direct connection to that Skype, right? If it is open. If it is not open, then I have to send a request to whatever, actually basically whatever address it comes, it will probably come back with the public address and some port number always, and it will just respond to that one, to that address and that port number, and in different, and so it doesn't have to go through the server again. Okay, yeah.
So if you're a hacker,
Yeah.
and you want a list of a bunch of people's computers that aren't behind NATs and probably have open ports, you just go to Skype and make your computer supernode, and then you've got a list of all the supernodes.
Well, it's much easier actually. You should take our course on security, where one of the first lab exercises we do is, we do lots of hacking exercises, and so it's very simple. I mean, if you just want to find what open ports are, you just run the program and you get the answers basically back. All you need is to somehow get out of your NAT box, so that your request will come back to you. I mean, you can do it from behind the NAT box as well, but it's much easier to do if you can do it from outside the NAT box. So you can sit right here and send out all the port requests, and you will get the responses back wherever the ports are open and things like that. So there are port scanners. So you don't have to become a super node to do this. Port scanning is straightforward. All right, by the way, all the NAT boxes allow you computers to be put here as well. So, except that when you are put here, then there are only certain ports that you can receive, which is similar to being here actually. So you could say that I have a web server, so port 80 will go to me, so it doesn't really matter whether you are here or here, port 80 will go to you, and so on. So that is not different. But all the routers today we come with NAT built in, and all these facilities you have programmed probably. How many of you have done port forwarding in your router? Anybody? Okay, so at least 1/10 of the class. And as you get more than one computer, you have to start doing that. If you have more than one computer, I mean, you have to have servers and all that. Yeah.
So what does this give you if you do that? All the traffic for a web server will go just to one computer? Or
okay, so here's the thing. Now let me tell you what I use server for. So I have an FTP server at my home. I have a printer. I have a storage server at my home, right? So if I'm here and I want to access any of those, how do I do that? In fact, one of the things I want to do is, anyway. So whatever I want to do, let's say I want to reach my FTP server. So that is on port 21. So I have to register that with my NAT box.
So it gives you access to an internal computer directly.
Yeah, direct access. Yeah, that's the last line. Incoming connections are possible only either you have registered permanently or registered on demand. Okay, so this is what is happening now. Port 80 is something that the firewall people cannot close. All right, they can close all other ports. So if suppose I did to my home, my home, and I said port 21, it could be just dropped here, right there, because port 21 is closed. Nobody is allowed to do FTP. Okay, but port 80 they cannot close. So every application in the internet today that wants to get inside a private network uses port 80. And so what you do is, most of, let me not say every, because that is a very strong statement and somebody will come up and say here's a counter example. So let's keep it simple. Most of them use port 80 nowadays. And And the others basically work on this principle that the client goes and registers with the supernode and the connection is permanent then. So the others work on this principle, that you have already opened whatever port it is, doesn't matter, you have a connection with the supernode and then anybody can get in through that supernode connection. Okay? All right. So that ends our P2P discussion. And the summary of this part of the chapter is that the P2P applications are more scalable, they are more efficient when the number of peers is large. Scalable means big. Basically, they can be used when there are millions of people. Server client can be used when there are hundreds of people. For millions, it becomes difficult, and for billions, it becomes more difficult. But P2P keeps scaling. Then BitTorrent, which is just one of the latest kinds of P2P, has peers, trackers, seeds, and leeches. Now you should know what is the function of the trackers, right? Everybody remembers the trackers. When you get a torrent file, the torrent file has the name of the tracker, along with whole description of all the files that are in that torrent. But so you can start somehow from there to get the list of all the seeds and leeches and all that. And then BitTorrent is designed so that automatically people who are close to you, they get connected to you. People who are far away from you get disconnected. And that is done by what is called optimistic choking. Optimistic choking means that you keep track of the top 4 and you do more communication with them, and then you do less communication with people who are sending less to you. Then we talk about distributed hash table are used to find information all over the world, and then the Skype uses the supernodes to keep track of active users, and for users behind the NAT it provides the relays. So that's the only way you can get into behind the NAT is by previously set up connection. Okay, so the homework 2D. Now is the time to ask questions if you have any questions. Homework 2D is, suppose Bob joins a BitTorrent, but he does not want to upload any data to any other peers. He is super careful, does not want to get an FBI notice. Actually, it's not FBI, it is Software Association something, I forget. So he does not want to get that notice. So what does he do? So Bob claims that he can receive a complete copy of the file that is shared by this firm. Can he do that or not? That's the question. And I will let you think about it. Now, what is your question?
About B?
B. Bob further claims that he can further make his free riding more efficient by using a collection of multiple computers with distinct IP addresses in the computer lab in his department. How can he do that?
My question is,
do
we assume that he uses a standard BitTorrent client, or can he use the protocol and manipulate it any way he wants?
Yeah, right. So I think in B he will have to manipulate the protocol a little bit.
So we can assume that he can.
Yeah. In the B you have to assume that. In A you don't have to assume that. In A it is a standard client. That's a good question. Okay. All right. So think about it, and that brings us to the end of and free riding. Actually, I don't want to say that answer. Okay, so all right. So the question is, this is the whole summary of the whole chapter, and the 5 points of the whole chapter. First thing we talked about was this whole business of TCP and UDP ports. So now you should all know what the ports are, how they are used, and so on and so forth. TCP and UDP ports. Then we talked about different applications, STTP, FTP, SMTP. They are client-server protocols and they use TCP connections. STTP is stateless, but cookies allow the servers to maintain state. So STTP as originally designed was stateless, and then the cookies were added, and there is a whole debate about whether you should have the cookies, whether you should allow the cookies, whether you should disallow the cookies. one thing, if you disallow the cookie, you cannot really do anything at all. And so the second thing you could do is you could clean up the cookies once in a while. What is the misuse of cookies, by the way? Can anybody think about what is the misuse of cookies? Yeah?
Like tracking between different websites that aren't related, but just have the same like ad networks.
Yeah. The ad companies keep track of what they do is, you are going to Amazon or Google or whoever, doesn't matter, but there might be a page there that has to be obtained from some other website, obviously advertisement, and they will put a cookie in your computer. So they will know the last time you looked up for the mortgage rate, right? And then they will send you an email saying that here is the mortgage rate, the best mortgage rate that you can find, or a credit card, or whatever you are interested in. And if you happen to go to any bad site for advertisement, then you can rest assured that your mailbox will be filled with the bad messages. So don't even try to go to any XXX places, because they just kill you from all sides. Okay, so that's the bad part of the cookies. And I mean, and not only that, they keep track of long term. They basically can join two things, that okay, this person is looking for mortgage, he's looking for a pool, he's looking for that. So they can make a very unique offer for you, that you cannot refuse. All right. So a lot of companies will say that you remove your cookies, but the problem with removing the cookies is, if you remove your cookies, then you cannot talk to your bank, because all the banks keep the cookies to remember that this computer is okay. All right. The minute you remove the cookies, you have to re-authenticate yourself. They will ask your mother's maiden name and whatnot, and where you were born, everything else, because they have never seen this computer before. Right. So I don't know. I think there has to be some selective method of deleting cookies. I haven't found one, so I don't delete any cookies. But there should be some selective method of deleting cookies, so that the cookies from the banks are not deleted, but the cookies from the advertising companies are deleted. Yeah.
Isn't that what like private browsing is on all these browsers now?
Huh?
Private browsing feature, it's maybe not hold that on every browser. But they have a feature you can turn on that doesn't.
Yeah. So I have that too. That is called ad block. Ad block recognizes the.
So in most browsers, you can enter in a certain mode where once you exit that mode, all cookies will disappear.
All
cookies, all browser history.
Yeah, right. That's bad. No, that's what I'm saying. See, that's the problem. That browser allows me to kill all the cookies, but I don't want to kill all the cookies.
Just for one session.
Huh?
Just for one session. So like any new cookies you got just for that session.
Oh, okay.
But the ones you
All right, for that session. Okay. All right. I haven't tried that feature, but basically I will have to restart a session, and generally I'm not even sure whether what is a session then? See, thing is,
what browser are you using?
Firefox.
Private browsing, Control-Shift-P.
That's the new session?
It puts you into that mode.
Okay. No. The thing is, because I have to get out of that mode, I have to probably kill the whole browser and then come back again. Control P again. Okay, doesn't matter really. This is not critical to here. The thing is that cookies have negative applications as well, and they are not very good. And so that's why we talked about here, is that they have some positive things, which is the state, and there are some negative things, which is keeping track of you. Proxy servers improve the performance by caching. So we talked about proxy servers, and then we talked about BitTorrent, which is a P2P file distribution protocol, and that we use, we talked all about this, how it keeps track of peers and all that.